Technology Overview. These slides were compiled by Rebecca Burton and Susan Arnold. The learning objectives for this module are to summarize the applied technology, that is, the application to work and related work tasks, and 2. Build process flow diagram linking work and work tasks to process, environment, and potential hazards. In subtractive manufacturing, you start with a unit of material and subtract the bits you don't want until you are left with a product and some waste. A visual example of the subtractive manufacturing process can be seen illustrated here, with a block of material being drilled away, leaving a usable 3D product and a large pile of waste behind. The term additive manufacturing, or AM, is meant to specifically differentiate these manufacturing methods from the more traditional methods, which are subtractive by nature. In its simplest form, in the additive manufacturing process, substances are combined to create a final product, and as a result, minimal waste is created. The process flow diagram, shown here, contrasts with the subtractive manufacturing method image shown earlier by beginning with a material and adding it to create a 3D object. In additive manufacturing, the only material you use is what specifically becomes the product, yielding much less waste at the end because nearly all raw material can be reclaimed. Feedstock materials come in the form of filament, wire, liquids, pellets, paste, and sheet metals. Finally, the ISO ASTM 52900 terminology standard defines 3D printing as the process of joining materials to make parts from 3D model data, usually layer by layer, as opposed to subtractive and formative manufacturing methodologies. The term is often used in a non-technical context, synonymously with additive manufacturing, and is now probably more common. The Wohler report, widely recognized as the defining informational resource for the additive manufacturing industry globally, uses the two terms interchangeably. Older terminology previously used to describe AM methods include additive fabrication, additive processes, additive technique, additive layer manufacturing, solid free-form fabrication, and rapid prototyping. There are many benefits to using additive manufacturing methods. These include reduced lead time because the parts are made to order, allowing manufacturers to respond to changing market conditions more quickly and vary production rates to align with demand. A recent real-life example is the use of additive manufacturing of personal protective equipment, such as face shields, during the early stages of the COVID-19 pandemic, when there were problems with the production and distribution of the products through traditional channels. Additive manufacturing facilitates the consolidation of components and reduces the number of steps to production, especially for early phases of the design and prototyping stages. Reducing the number of components also reduces the time and labor needed to make the part, resulting in reduced developmental costs. Additive manufacturing reduces the amount of waste because products are built layer by layer and unused feedstock materials can be reclaimed and reused. In addition, the manufacturing methods themselves allow for easier customization and production of complex geometries. Unlike conventional manufacturing, such as casting or molding, in which equipment and equipment parts must be pre-manufactured, acquired, and installed in the machine before parts can be produced, the computer-driven digital design and layer-by-layer method of additive manufacturing is more nimble and flexible in what is produced. With additive manufacturing, the low cost of setup makes low-volume production economically feasible. If problems are found with a prototype, corrections can be made quickly and new prototype produced. AM systems use thin, horizontal cross-sections from 3D models created by computer-aided design, or CAD, software. 3D scanning systems, medical imaging equipment, and even video games to manufacture objects one thin layer at a time. Concept modeling and prototyping were the first applications for parts made by AM. They allowed designers to communicate their design intent and clarify ambiguities from CAD models and engineering drawings, and can be used for presentation at meetings with management and customers. These prototypes can also be used by engineers to test form, fit, and function. But over time, the applications have expanded as quickly as the technology has advanced, both in terms of the applications themselves and also the materials available to print. Applications include extrusion, jetting, photocuring or photopolymerization, laminating, spraying, and thermal fusion. The following slides show examples of products created from these most current applications. These images shown in this and the following slides illustrate just a few applications of additive manufacturing that are already on the market. The sand cores shown in this image are used for casting and were produced using binder jetting additive manufacturing. Metals, and most commonly cobalt chrome alloys, are used for dental reconstruction because of its strength, corrosion resistance, and biocompatibility. In this example, laser sintering was used to build a titanium implant at about 20% of the cost of a milled implant. The application of additive manufacturing is ideal given its ability to deal with small, complex parts that must be customized to the individual. In this image, an additive manufactured surgical guide facilitates a precision application of digital dentistry. The end result is greater accuracy in placement and higher quality outcomes of complex dental procedures like dental implants. This image shows a 3D printed modular furniture cabinet. In April 2019, researchers at Tel Aviv University printed an engineered heart model using the patient's cells and other biomaterials. Printed organ contains cells, blood vessels, ventricles, and chambers. There probably is a horizon to the list of applications for this technology, but we haven't hit it yet. In this bar chart from the 2020 Wohler report, you can see that aerospace at 16.8%, medical and dental at 15.6%, and automotive at 14.6% are the largest industries using AM. Customer applications are broken by category in this figure, from which you can see that the top three categories of education and research, functional prototypes, and end-use parts represent almost 70%. The chart on this slide indicates revenues in millions of dollars for AM products and services worldwide on the y-axis and the year on the x-axis. As you can see, the industry has experienced significant growth in the past 10 years. The market has grown by more than 11 times between 2010 and 2020. The lower blue segment represents products, and the gray segments represent services. These categories exclude secondary parts and processes such as molded parts or casting. This graphic shows the accelerating rapid proliferation of industrial AM systems manufacturers and the number of systems they're selling, shown in the blue line. The number of manufacturers exceeding an annual sale threshold of 100 machines is indicated by the pink line. An industrial AM system is defined as one that sells for more than $5,000. This graph shows the rapid growth by number of industrial systems sold each year since 1988. Since 2012, the number of industrial systems sold has increased by 800%. Given the explosive growth of this emerging technology and wide-ranging applications, understanding the technology, its potential health hazards, and exposure opportunities is essential knowledge for industrial hygienists supporting these technologies.